Hello everyone. In this video we're going to be talking about something called total internal reflection. Now in a previous video I've said that when light travels from one medium to another it changes speed and is refracted. So the word refraction referred to the bending of light. But what we have here is a special type of bending, if you like. If the light rays travel from a less dense material to a more dense material, they're refracted to what's called the normal. And you get the opposite with vice versa. So if they're travelling from a dense material to a less dense material, they're actually refracted away from the normal. So before we begin, what I want to do is just draw a very quick sketch of something here. Now I want you to imagine that we've got a piece of glass here, and outside this is the air. So we're going to imagine that we're refracting light from a dense material, the glass, into a less dense material like the air. So in this instance we're going to bend that light away from what we call our normal. Now the normal is given as this straight line that's perpendicular to the material, so at 90 degrees if you like, to the surface of the glass. So we have, and I'll draw this in red, we have our incident ray there, and then we get this refracted ray moving off away from the normal, if you like. So we said that this was our refracted ray, this was our incident ray, and we've got two angles. And now to understand total internal reflection we need to put this in place. This angle, if you like, in yellow, and then this second angle here that I'll shade in green. Now the angle in yellow is the angle of incidence, so we'll put a little I by that for the angle of incidence, and the angle that I've shaded in green is the angle of refraction. Now this is what happens when the light rays move from a more dense material to a less dense. They're refracted away from the normal. Now for total internal reflection to occur, the light must travel from a dense material to a less dense material, like glass going to air or water going to air. So the first thing to say is that for this phenomenon of total internal reflection, we need the light to go from a more dense to a less dense. So we'll just make a note of this key thing. We need to go from more dense to a material that is less dense. That's critical. Now, as the angle of incidence increases, so does the angle of refraction. And when the angle of incidence actually reaches a known value that's referred to as the critical angle, then what you see is this refracted ray actually travelling along the surface of the medium that it's travelling in. So in other words, the light is refracted at an angle of about 90 degrees. Now for this glass, the critical angle is about 42 degrees. So let's draw what that would look like down here. So here's our glass. Let's put our normal in place. So here we have the incident ray, like before, but now what we see is that the refracted ray travels along the sort of edge of the glass. Now what that means is that this yellow angle here, and I'll shade it in a sort of hash there, this angle now that I referred to as the angle of incidence before, that's become our critical angle. Because at the critical angle, that's when the refracted ray goes off at 90 degrees, away from that normal. So we've got a critical angle, and as we said, it was about 42 degrees for glass. Now, that refracted ray, as I've said, travels along the surface of the denser medium in this case. But total internal reflection happens when the angle of incidence is greater than the critical angle. When the angle of incidence of the light ray is greater than the critical angle, then no refraction takes place. Instead, all of that light gets reflected back into the denser material, in this case, the glass. And this is what we mean by total, so for all, internal reflection. So all of that light is internally reflected. So let's finish by drawing what this would look like. So here's our glass. Let's put the normal in place. This time, I'm going to just draw a sort of hashed red line to show the original incident ray, whereby we achieve the critical angle. Now we're going to imagine that the incident ray is coming in at an angle greater than the critical angle. So I'll put IR for incident ray. In yellow, here, I'll show the critical angle. But now in a slightly darker colour, I'll put in this, or I'll colour in this portion here, because that bit in red that I've just coloured in, that's how much over the critical angle we are. So we're over that 42 degrees. And then what we get as a result is this time a reflected ray. And this, therefore, is total internal reflection. Now, if we were to summarise this or think about it in terms of two key points, in order for total internal reflection to take place, the rays of light must, number one, travel from a dense medium to a less dense medium. So this point at the top, that's critical. And for number two, so I'll make a note of this down at the bottom, as the second key point, the angle of incidence so the angle between that incident ray and the normal, that angle of incidence needs to be greater than the critical angle. So the angle of incidence needs to be, and I'll do the greater than sign, greater, and really highlight that, greater than what's called the critical angle. So the two key things to get total internal reflection. The moment that incident ray is beyond the critical angle, in which case 42 degrees for glass, rather than bending out from away from the normal when it's going from the more dense to the less dense medium, that ray of light is fully reflected inwards. It's totally internally reflected. And things like optical fibres make use of this total internal reflection. In another video, we're going to talk about the physics behind optical fibres. Okay, hope all that helps.